You got that straight?
Yes. I don't like the looks of this at all.
That's good.
Okay, tonight for our short presentation, Jeff McLeod is going to be speaking. He's only been a member of the club for less than 2 years.
Less than 2, yeah.
And now he's the secretary, so if he can do it, you can do it.
Please do.
He, I think, has a demo of some of his
That'll be at the break.
at the break. He'll need a little room to do it. So watch your stuff. His career plans include being a planetary geologist and lunar resident. In his free time, he's an artist, juggler, and unicycling street performer. And tonight, his topic is the distance to the moon.
All right, I hope you guys aren't all tapped out on eclipses, because we're going to talk even more about them. And basically, this all started, I think, with a conversation that I had with you. I think we share an interest in ancient astronomy and replicating some of the experiments they did. For me, it's just the only experiments I can do because I don't have the capital for huge telescopes. So ancient astronomy is a nice, cheap way to get distances for things. So this is the first of the tetrads that happened last year. It was April 15th, and I don't think anyone saw it here. We were pretty clouded over. And for those of you that never heard the story, I took the day off of work, the following day, so I could stay up all night. And it was supposed to be cloudy, so I figured, well, I'll drive out to Ann Arbor, it'll be clear, no big deal. And then I was like, well, I'll drive to Grand Rapids, it'll be clear, no problem. Well, then I'll drive to Chicago, it'll be clear. And then I ended up somewhere in Indiana, and it was finally clear. So, unfortunately, this is the best photo I got, just putting my phone up to my telescope. I wasn't really there for telescope observing. What I was trying to do is time intervals of the eclipse. But as I drove out there, I got this really nice layer of ice on my car, and I almost crashed twice on the way out there. It was not the most fun drive. And then after the eclipse, I figured I was close enough to Wisconsin to go see the Yerkes Observatory. So I went out there on very little sleep, and then I visited my buddy on the farm and got my hand licked by a cow. And then I figured I was close to Chicago, so I went to their ledge and did a handstand, because that's the kind of thing I do. So I was very prepared for this eclipse, and you can tell because my notes are taken on the back of an envelope, and that's how most astronomers do their best work. Yes?
I have a question.
Yes?
Are you related to Gary Ross?
I was going to mention, there is very little electricity.
We share the same good looks.
That's right.
We could be close relative.
I'm gonna have to research into
You're
it.
actually except for Gary.
So this is basically kind of my scribble scratch of what was going on. I kind of tried to predict at what point the moon was halfway into the shadow to kind of help me average my times. And so basically what I did is I started my first timing right as the moon is entering the shadow. And what I'm trying to do is determine the time that the moon is crossing its own angular distance. So the end of the first timing is when the moon is completely in the shadow. So this is totality. And then that begins the second timing where you're actually measuring the time that it takes the moon to traverse totality. So then that would be the ending of the timing. But I knew that Gary Ross would not approve of me using a digital timing device. So when I got home, this is my initial number crunching on the arithmetic, and I'm not going to go over the math. Just really not. It's pretty simple. We'll go over it. But anyway, so when I got home, I decided to make a clock so that I could use my own clock rather than a digital clock. And after much contemplation, I decided on a very rudimentary water timing clock rather than a true water clock. And basically how this works is you have a main tank going to my distribution tank with an overflow. And this isn't my actual measuring device, but that's just what was in place when I was taking the photos. And if we go closer here, there's an overflow line so that the water is always at that same level. So there's no change in water pressure as this is counting down the minutes because it has to run for about 3.5 hours to get the measurements that I want. So that gave me a weight or volume of water per the timing that I made, but I needed to be able to convert that into a useful ratio between the Earth's shadow and the moon. So we built a very simple cantilever, kind of something like this thing. It doesn't look like it, but those are just barely off the ground. And so I've got a significant amount of water. This would be the heavier one, is the shadow time, that's being the moon time. But of course, the buckets have mass to them as well, so I needed to take out the weight of the bucket so that I was just measuring the water. So that's just the ratio between the two. And then this one is the ratio between an empty bucket and the time it takes the moon to cross its own diameter. So this gives me a unit of measure that I call an empty bucket. So in the future, we'll all be weighed in empty buckets. So after kind of taking all of that into consideration, I got a ratio of 2.3 to 1. So what I measured, the shadow of the Earth is 2.3 times larger than the moon is, which is close to what it actually is, especially considering that I'm using a water clock. So that brings us to the eclipse machine. The other factor in making this calculation for the distance of the moon is you need to know the rate at which the shadow of the Earth is tapering to nothing, which is a very narrow taper. So we decided to put a bowling ball up on a ladder. And so by taking a string and then dividing by pi, we got a really accurate number for the diameter of the bowling ball. And then the shadow falls into our kind of like little eclipse box. And we're measuring how small that shadow gets over a certain distance. I put a string attachment point on the side of the ball, and so we ran a string from that point to our measuring board to give us the distance and then the difference between the measured shadow and the size of the bowling ball. So there's just kind of our box. There's a board that's in there using those, there's 2 nails at the top of the board that we use to orientate it so that it is exactly facing the sun. So this is just a look at that board. We put some paper on it. how am I doing on time? This is just a look at the shadow when I'm looking into the box. You can tell it does get pretty fuzzy. And then this was my notes. You can see we made 4 measurements as the sun was setting and averaged them out, and I got a ratio of 109.3 to 1. So that means if you have a 1-foot ball, the shadow will be 109 feet long before it completely disappears, which is within 1% of what I looked up online. So I was pretty satisfied with getting that kind of accuracy out of a bowling ball. And so basically, you compute that slope, and the only thing that I wasn't able to do was determine the size of the Earth, so I borrowed Dr. Parton's information on that, which is something that I'd like to do at a later date for myself. And so you simply times the Earth's diameter by 109, and you get the length of the Earth's shadow, which I'm saying is 829,000 miles. If you disagree, do the measurement yourself. One of the other crucial happenstance that we're just lucky to be in the system that we're in is that the moon is roughly the same angular size in the sky that the sun is. If that wasn't the case, this technique wouldn't work. Because of that, the angle here is exactly the same as the angle to the moon. And because of that, there's a kind of symmetry between the correlation between the shadow of the Earth and the moon and the distance to the moon versus the entire shadow. Which you can completely ignore that math there because I didn't do it right. And basically all you need to do is divide the total length, which is C, by 3.31, which is that 2.31 is the ratio that I got between the Earth's shadow and the moon's diameter. So I ended up getting 250,000 miles to the moon, which is, it falls within the distance that the moon is either at its closest approach or its farthest distance away. It's kind of 5% from the average, which I was pretty satisfied to get 5% without using electricity or Google, Mr. Ross. And another thing that you can do with this information is then you can use that slope to give you the diameter of the moon, which I calculated to be 2,200 miles, which is also right around 5% from what NASA told me it was. And so some future plans that I have is determining the size of the Earth, hopefully within the same margin of error, determining the orbital period of the moon to within 10 minutes, maybe 5 minutes, I don't know yet. And then I've got theories on determining the distance to the sun using a total solar eclipse. I'm not exactly sure if it's going to work or not, but if I can get good data at the 2017 eclipse, hopefully I'll have a talk on that. That's it. Questions?
What was the true diameter you got?
2,200.
All right, what I learned back when I was a laddie, it was 2,160 miles in diameter.
Correct.
Yes.
The Earth is 78.
Yeah, I thought the Earth was, yeah, something like,
78.
That was not 18 years.
Yeah.
Ancient.
it was derived in the 1940s. Right.
I think we're going to have to
All right.
hold any additional questions for the break if you'd like to talk with Jeff.
Excellent.
And don't run over anybody on your
Well, I'll be
up here.
Yeah.
So
I'm much more comfortable on top of the 6-foot unicycle behind the podium.
All right, so it is break time. You have snacks here. You are welcome to donate money. Gary Ross brought the snacks today. And if you would like to donate snacks in the future, you will be reimbursed up to $20 by the club. Enjoy.
I didn't know you had it.
Yes, I did. Yep.